let's get specific and look at confidence intervals of means. And if you wonder what this means, then you just missed a bad pun. So going into our basic sketch of a formula, we have our parameter, and we said that when we're talking about means, we're trying to estimate mu. What is the population mu? The statistic is our best guess, which comes from our sample, and that's going to be x bar when we're talking about quantitative information. So we go out, we take our sample, we average our values together, that is going to be x bar. Then we have plus or minus our margin of error, and our margin of error is made up of the standard error and z star, our number of standard deviations based on our confidence. So the standard error in this case comes from the central limit theorem. So we take our standard deviation divided by square root of n. That's our new standard deviation, also called the standard error. We also have this critical value here, this z star, and we have a little table that you can just kind of write these values down. You could calculate them using inverse normal in your calculator, working backwards from a normal CDF, but it's a lot easier to just take for granted that these are the number of standard deviations you have to go in each direction to get the middle 90, 95, and 99%, the values we use most often. Again, this comes from the central limit theorem. Before we try to use this formula in any situation, we have to be aware that there are some conditions to using it. We cannot just use it in all situations. The first one is that the data comes from a random sample, and we're used to that. Even with StatKey, when we're doing simulation, we need to make sure that we have good data, because if we put bad data into a good formula, it's going to give us bad results. So we need to make sure it's random. And SRS is always good. Stratified, systematic are going to be good. If it just says that it was random, that's usually acceptable. Second one is getting back to the probability situation. It says population size is 10 times the sample size. The reason we might care about that is that if you think of probability, let's say a jar of marbles, and you have so many red and so many blue marbles in the jar. Or in this case, let's do 3 purple, 3 blue. So this is a small sample. If you think about drawing one out, you have a 50-50 shot of getting blue or purple because there's 3 of each. But once you draw one out of the jar, now it's no longer 50-50 odds. And when you're taking samples, you draw out of the jar and you don't put that person back. You keep them out. You don't want to sample the same person twice. So because the odds are changing with a small sample size, it actually can affect the shape of that normal curve. When you have a large enough sample size, that change is so small that it actually doesn't matter. So that's what we're kind of worried about here with this population size. So it's just an estimate. Make sure that you have a large population. And then the last one is specifically focusing in on the sample. And so it says we need to have a sample size n that is greater than or equal to 30. Now again, that's not a hard and fast rule. It is more of a rule of thumb. So if you have a sample of 29, it's probably going to be okay. If you have a sample of 33, it doesn't mean that it's for sure perfect, but it's probably going to be okay. But 30 tends to be that number where no matter what your initial distribution was, you should be good. So now let's jump into an example to try to use this here. It says, while touring the bobblehead factory, you took a random sample of 34 bobbleheads. The average weight was 302 grams with a standard deviation of 12 grams. Find a 95% confidence interval for the population average weight. Well, since we're finding a confidence interval for a mean, we want to check our conditions right away first to make sure that we are actually able to do this. First condition says we have a random sample. And if we're checking here, it says that we took a random sample of 34 bobbleheads. So we're good on that first one. Second one is that the population size is 10 times the sample size. If we're at a factory, I would assume that a sample of 34 is not going to be greater than a tenth of the factory's total output. I'm guessing this factory produces quite a large number of bobbleheads. So We don't know for sure, but I would say that condition is probably met. And then the last one to check that we have a sample greater than or equal to 30. If we check our problem here, it says we have a sample of 34. So not way in the clear, but 34 should be okay. It should be a safe number. Now let's look for the pieces that we need here. We want to find an estimate for the population mean, which we call mu, right here. So we want to estimate that. And to do so, we need to start with our sample average. And it says the average weight from our random sample was 302 grams. So that is our starting point. So 302 grams. From there, we need to figure out our margin of error. And to do that, we look at our new standard deviation, which is going to be our original standard deviation here of 12 divided by the square root of our sample size. So if we take this plus or minus, we're going to have 12 on top over the square root of our sample size of 34. And then we have to multiply by z star, and that depends on how confident we want to be, which in this case, at 95%, we can peek back at our chart, and we'll see that that's going to be 1.96. So if we plug in times 1.96 here, we will have our full margin of error statement. So we can clean that up when we plug that into our calculator. We have 12 divided by the square root of 34, and that's going to give us our new standard deviation. We take 1.96 of those in each direction because we want to be 95% confident, and we end up with 4.03. And what we're going to do is we're going to say that based on the other precision that we're given here, 4.0 will be more than precise. So we have 302 plus or minus 4.0. That's going to be then the margin of error. And that is a confidence interval of a mean.